you can either bring it physically or written down, or send it typed down by email. Yeah. Okay. And then there will be no final exam. The grade will be based only upon the home assignments, and it will be just the percentage of, it will be about maybe 70 problems altogether, and if you solve like 35 of them, you get the grade 5, which is 50% of solved, right? Okay. Now my name is Michael Finkelberg. As far as I understand, simultaneously with this course, there is another course on number theory by Alexander Kalmynin, somewhere nearby. And I strongly recommend you to go there. I am sure that it's more interesting. And Alexander Kalmynin is a really great young mathematician working in number theory. I do not work in number theory, so you will not be able to work with me, but you will be able to work with him. So once again, I strongly recommend you to go there. Right now, maybe starting next time, think about it seriously. Now, as for p-adic numbers, I will certainly define them in very detailed way in well, 15 minutes. But let me just say that the field of rational numbers is embedded into the field of real numbers, and this is just the completion of Q with respect to the usual Archimedean metric. And similarly, there are some other metrics numbered by primes, and the completions of rational numbers with respect to these metrics will be p-adic numbers. Well, probably I don't have to advertise the real numbers. They are all over around us, and you cannot really count anything. Well, I mean, to count something you need just positive integers, but if you want to, well, compute some integral or whatever, you certainly need real numbers. The p-adic numbers were also introduced by Kurt Hensel around the break of 20th century, just to make some computations, and they play, well, a similar role. So I will explain all this in detail later on. But somehow, today we will prove the philosophically important theorem by Ostrovsky that says that this is the complete list of completions of Q. So it's a classification of norms on Q. There is just one Archimedean norm and non-Archimedean norms numbered by primes, and that's it, nothing else. Now let me give a few examples of problems that are solved with the help of p-adic numbers. I mean, that cannot be solved without the use of p-adic numbers. As I said, if you want to count some areas or whatever, you need really real numbers. And I will give you problems that, in fact, since they were introduced like 120 years ago, they became one of the basic objects of number theory, of arithmetics. and in particular, there are many, so they became interesting in themselves. And there's a lot of problems about p-adic numbers, and like 70 of those problems I will give you this semester. But certainly, before you know p-adic numbers, you are interested somehow, why should you study them? So there are some problems that do not mention p-adic numbers, but whose solution requires use of p-adic numbers. Let me give a few examples of such problems. So none of them will mention p-adic numbers. The first one is about multiple zeta values. So I'm sure everybody knows the Riemann zeta function. The sum of n to the power negative s, where n is a positive integer and s, well, must be bigger than 1. Otherwise, this series does not converge. But in fact, we will be only interested in the case when s is also a positive integer, but it must be bigger than 1, so s is at least 2. And then probably you know that if s is even, then this one can be computed explicitly. Do you know? Yeah. For example, zeta of 2 is pi squared over 6. Yeah, and zeta of 4 is pi fourth over 90. And zeta of 3 is nobody knows what. At least it was proved like 40 years ago that it's irrational. But apart from this, nobody knows anything at all. Well, this computation was done by Leonhard Euler, and certainly he was interested in this, but being unable to compute it in the same spirit as those, he tried various approaches, among them multiple zeta values. So he defined zeta over S1 and so on, Sk. Here again, Si is an integer, and if you want the convergence like here, you impose that S1 is at least 2. Okay, and then this multiple zeta, it is equal to the sum over integers n1 bigger than n2, bigger than so on, bigger than nk. They are integers, just the same, n1 negative s1 power, and so on, and k to the negative sk. Okay, and then again, Leonhard Euler proved many things, starting with zeta of 3 equals zeta of 2, 1. Okay, but somehow it didn't help him to say anything useful about zeta of 3, unfortunately. But he started this subject, and now there is a theorem due to Francis Brown about 10 years ago that considers the whole variety of those multiple zeta values. So you consider the R vector space, Q vector space, well, maybe let's call it Z for zeta values, and it is subspace in R, but R has an uncountable dimension over Q, and this is a subspace of countable dimension, and it is spanned by all the multiple zeta values. like this. Okay. Now, the theorem says that Z is actually spanned by multiple zeta values S1 and so on, Sk, where all S sub I is either 2 or 3. Any question or comment or anything? No? No? So this is the Euler theorem is the first example of this Brown theorem. So this guy has 2, 1, and it is expressed via that one that only has 3 with rational coefficients, namely with coefficient 1. Okay, and well, there is a conjecture that those guys, well, Si equals 2 or 3, form the Q basis of Z. So there are no rational relations, additive relations. Okay, this is the first example of a problem which absolutely cannot be solved without p-adic numbers and real numbers. So it starts like a problem in real analysis, though all s's certainly are just integers, but still, just to define the sum, you need convergence in the field of real numbers with respect to Archimedean metric. So you cannot even pose this problem without real numbers. But the solution also requires the use of p-adic numbers. Okay, in fact, it requires many other things, and the solution, well, if you write down everything you need for a solution, certainly it takes more than 1,000 pages. So it's a very difficult and deep theory, which uses a lot of things. Okay, now another example is in the realm of modular forms. So it again starts within real analysis, but you consider the so-called delta function of Q. This is Q times the product over positive integers, 1 minus Q to the power n to the power 24. Yes, and well, you can expand this infinite product as an infinite sum. Tau of n, Q to the n. Well, it's divisible by Q, so it starts with 1. Okay, now there is the following conjecture by Ramanujan. Well, it's around maybe 20, I don't remember. That was proved by Pierre Deligne. No. Well, in 2 installments. And it says that if P is a prime, then the coefficient, the corresponding coefficient here is not more than twice P to the power 11 over 2. Okay, and if you say 12 over 2, just 6, then it's in a sense elementary and can be proved without any p-adic numbers, just in the framework of real analysis, complex analysis, I would say. But if you want this sharper estimate, then again, no way to avoid p-adic numbers. And again, the whole proof is at least 1,000 pages long. It's a very deep and difficult theory. It's 50 years old. Okay, and then maybe one last example is so-called Sato-Tate conjecture. That was also proved by many people. It's a theorem by Richard Taylor and many co-authors. Well, you take an elliptic curve. Do you know what is an elliptic curve? Everybody? Not everybody? Not everybody. It's this. Do you know what is projective plane? Not either. But then maybe maybe it will be hard for you to follow the course. So it's certainly up to you. But
I know what is projective plane.
You do? Ah, then fine. Okay. So then it is given in homogeneous coordinates just by a cubic equation. So it's a set of solutions of cubic homogeneous equation. So usually it's written in the form y squared z equals x cubed plus ax z squared plus b z cubed, something like this. So it's a homogeneous cubic equation. Okay. So now assume that that a and b are some integers, and the discriminant is not zero, so the whole thing is smooth, and E is smooth. Then for any p, again prime number, you can reduce everything modulo p and obtain a cubic equation over z modulo pz, which is just the finite field with p elements. And by the way, where is the list? There is the list. Everybody is inscribed. Very good, thank you. But you didn't write your first name. Not that I don't know it, but for example, if you submit your home assignment without your name, then it will not be graded. Yeah. Okay, so it has just finitely many solutions. Of solutions in P2 of Q. Then it is another very important and old theorem, maybe like 100 years old. And it says that this number of solutions is equal to 1 plus p minus square root of p times something, alpha p plus alpha p bar. So here alpha p well lies in the unit circle, but maybe in the unit half circle, I should say. So here you have alpha p, and you want certainly this to be an integer, in particular real. So this alpha p just is complex conjugate, alpha p bar. Yeah. Okay. Well, oh, sorry. It's p, yeah. But then certainly it's a subfield of fq, and you can also ask for number of solutions in the projective plane over fq, so you can extend the scalars to some finite extension of fp of the base or the prime field, and then again it will be equal to 1 plus q minus square root of q times alpha q plus alpha q bar, and this alpha q will be well, if q is p squared, this will be alpha q will be alpha p squared. Okay, so it will depend exponentially on your size of your field. So what I want to say, that this alpha p lying on the upper semicircle is characterized by its angle phi p, its argument. And the question is how those arguments are distributed for various p. So this Sato-Tate conjecture, proved by Taylor, Sheffield, Baron, and others, says that phi p, as p runs over the set of primes, is uniformly distributed on this upper semicircle with respect to the measure 2 over pi sine squared phi d phi. Okay. Now, again, this is a very difficult and deep theorem, and again, the whole proof constitutes more than 1,000 pages, and the use of p-adic numbers is unavoidable. But I wonder if this measure rings a bell with somebody. Why such a weird measure? Well, this coefficient is just normalization, so that the whole measure should be 1. But why such a measure? I mean, probably the first idea is that it should be uniformly distributed with respect to the just measure 1 over pi d phi. but not. And why not the simplest measure, but such one? No, the imaginary part of alpha will not be distributed with respect to this natural measure either. So I mean, this measure is natural, but in what sense? That's my question. Well, so let me just make a comment. What is this measure? Well, alpha pi does not come by itself. It comes together with its conjugate, and the two of them make the two eigenvalues of a unitary operator. So, alpha pi and alpha bar pi are eigenvalues of a unitary operator in SU2, right? Defined up to conjugation, right? When we know the eigenvalues, so they determine a unitary operator up to conjugation. Okay, now do you know what is SU2? Right, it is S3, but anyway, it's a group, so it's a very symmetric substance, and in particular, it carries a Haar measure, which is left, and it's a compact group, so it has a Haar measure which is left and right invariant. But then you can rewrite integration over this Haar measure just as an integration in terms of eigenvalues. And this will be this measure. So 2 over pi sine squared phi is the Haar measure on SU2. Okay, so it is really the simplest invariant measure, but it is written in some economical way. So you can integrate over the whole sphere S3, and there the measure will be absolutely symmetric with respect to all the rotations of the sphere S3, but you write it down in terms of eigenvalues and you obtain this. Okay. Well, you have SU2. If you quotient out by the conjugation action, yes, this will be just this interval from 0 to pi. And if you just push forward your Haar measure, you will get that. Maybe pushed forward. To 0 pi. Okay, so these are examples of very deep and difficult problems that unavoidably use p-adic numbers. All of them also use algebraic geometry, and this is what I am actually working with. So unfortunately, I'm only layman in number theory, but I work in algebraic geometry. And that's why I like those problems. Okay, now let's go back down to earth and define actually p-adic numbers. So certainly Kurt Hensel at the turn of 20th century gave some formal mathematical definition, and I will give it in a few minutes. But so to say, philosophically, the existence of p-adic numbers is due to the basic rules of arithmetic, like, say, adding integers or multiplying integers, or maybe division of integers. So when we consider, say, two large integers like and then you want to add something else, like something like this. Then in our world, say, of finances, we're only interested in the order of magnitude, right? So we're interested in the left hand part. But when they teach us in high school or preschool, we actually do the addition from the right. So it'll be like 9, 4, 6, and so on. And this is sort of philosophical contradiction. We're interested in the left-hand part, but we must perform the addition starting from the right. And the p-adic numbers, they, in a sense, solve this contradiction. So for p-adic numbers, the most important part is also on the right. Then, in fact, you can go to the left as far as you wish. So you don't have to step anywhere, right? If you consider the numbers that go indefinitely far to the left, then our high school rule of addition perfectly fine works with them. Okay, you just continue like this. It's 4, and then 2, and then 0, and so on and so on. So like 10 adic numbers, well, are the usual numbers, say integers, integer. The usual integer numbers that can go infinitely to the left. So well, with the usual real numbers, say you can place some pointer here and then continue to the right indefinitely far. Okay. With p-adic numbers, if you want rationals, you can also put a pointer, but then you continue only a few points to the, well, a few digits to the right, but indefinitely to the left. Okay, so you just swap the usual importance. The farther to the left, the less important is it 10 adically. Okay, so now 10 adic rational numbers. can have finitely many digits to the right over the pointer. Okay, and you can add them, you can multiply them, but you well, with division there will be some problem. So the division for 10-adic numbers is not always possible, but well, we use the base 10, right? But we could as well use base 2 or 3 or 4 or whatever. Now, if our base happens to be prime, then division will be possible as well. But if our base is p, 3, 5, and so on, then the division is well defined as well. So I mean QP will be a field. Okay, and well, this is related to another problem which also does not involve adic in its formulation, but in fact almost does. So the problem is when a usual integer, when you square it, it ends in itself with itself, so to say, or at least ends the same way as the one you started with. I mean, like 5 squared is 25, and this is good. And then 25 squared is 625, and again they have the same end part, and you can continue like this, or else, for example, 6 squared is 36. Again, you have the same end part, and can you continue this? Like 5 continues to 25, and then 625 is also good. If you square 625, it will end with 625. But what about 6? Can you continue 6? For example, if you square 36, what will you get?
Yeah, it will, because we will multiply 6 with 6, so in the unit place we will
I mean, yeah, 6 is fine, but if you want it, if you wanted to have more digits, then can you find something which?
It's 1296.
If you square 36, so 36 does not work. And does anything work ending with 6? Can you find any, say, 2-digit number whose square will end with itself? And what is it?
Not sure, because much as I remember,
Yes.
the 6 integers.
Also, you may speak in Russian if you prefer. Yeah.
So much as I remember, it composes a product of the 2 and the 3.
Yes, it's true. Yeah, and so what? I mean, there is nothing 6-adic or 5-adic or whatever about this so far, at least.
Remember, the idea is that
But you don't need any ideas. You just need to multiply. Right. Absolutely. Yes. 76 squared is, I don't remember what, but at least it ends with 76. And do you know the actual value of 76 squared?
5,776.
9,000, what is it? 5. Like this. Okay, so 76 works. And then in your first home assignment, you will have a problem about... No, you can extend. You can extend. I mean, the next one will be 376. If you are asking about this.
I asked about 2-digit numbers.
Yeah, that's it.
Yes. Of course, there are infinity many, I suppose. If we если мы берем сколько угодно, скорее всего, бесконечно много.
That's true, but not evident at all. In fact, you can continue like this and like that, but it's not evident at all. No, it's uniquely defined. No, you can only continue like this and only like that. It's uniquely defined. Well, certainly you can start with 0 and also 1. So in fact, what we're doing, we're solving the equation like this in 10-adic integers. That's what we're doing. And I claim, and this will be the content of our very first problem, that there are just 4 solutions. This, that, and well, something like this, something like that. Just 4 solutions. This is very much related to the fact that you cannot divide 10-adic numbers, because it turns out that this is just the direct product of those guys. Right, just as the Chinese remainder theory. And now, that's why it has 0 divisors. And that's why you cannot divide. But then, this thing is embedded into the field of fractions, Q2. And in the field, any polynomial equation can have at most degree number of solutions in the field, right? That's probably you remember from the high school. So there are at most 2 solutions here and at most 2 solutions there. But then you can take their products. So if you take 0, 0, you will get this. If you take 1, 1, you will get that. But if you take 0, 1, you will get this. If you take 1, 0, you will get that. Okay, this is some scientific solution, but you also have to do this in an elementary, straightforward way in your home assignment. Okay, so let me now give a formal definition, but before I forget, I hope that in my prerequisites list there was mentioned something, yes, like Galois theory. So you do know Galois theory. You do.
I do.
You don't. You do. You do. Ah, very nice. So the formal definition is as follows. So you can take any n, well, maybe at least 2, but then soon we will require it to be prime, but maybe not from the very beginning. And then you just consider your digits going from the right end. So far we speak about Zn, just integers. Then we will speak about division, but we start with integers. So what is this? well, you have the rightmost digit, and the rightmost digit lies in z modulo nz, right? It's in the base n. Then you want the two rightmost digits, and well, you can say that it's just a couple, one digit in here and another one also in here. But if we want to get the result, which is obviously equipped with addition and multiplication, we want to carry this ring structure with us through all the process. So what would you suggest for the rightmost two digits step? The rightmost digit, the one rightmost digit lies in this ring, but the two digits carry information about what? About which ring? Right. And then you can forget the second digit from the right, or else you can just project like this from this quotient ring to this quotient ring. Okay? And you continue like this. It's z over n cube z. Again, it's surjection, and so on. Okay? And the formal definition is just the so-called limit or inverse limit of this system. And do you know what it means, or shall I explain the meaning? No?
We know.
Okay, fine, great. So it's the set of sequences that are compatible with respect to those maps. In particular, you don't have to know any particular term of this sequence if you know the previous ones to be just obtained just from the projection. So you can forget any finite part, or any part at all. Fine. And then, since all those guys are rings, certainly the limit inherits the natural ring structure, or commutative ring. In particular, with unit. Just if you take units everywhere, there you are. Fine. And now, now you want to say that n is a prime, and you want to define the field of fractions. In fact, to obtain the field of fractions, you only need to invert p itself, and everything else is invertible already. Well, at least you have to invert p, but in fact, if you invert p, everything will be already invertible. So we want to invert p. And how do we do this? Well, certainly we can formally write that you take zp and you just adjoin 1 over p formally. But you can also do this, so to say, informally. Pardon me? Yes, this is localization, yes. But you can somehow state it in very similar vein. How can we state it in very similar vein? Well, you can, in a sense, dualize this. So you certainly have the projection from z modulo n squared to z, but also have an injection from this into here, right? These are just all things in here divisible by n. And this embeds into z modulo and cube z, and so. Okay, and now what you can do is take the co-limit of this thing. Do you know the meaning of this? Direct limit or co-limit? Everybody knows. Fine. And then what will you get? Yes, right. It is something dual, absolutely. But unfortunately, it's not quite a ring anymore because those embeddings do not preserve the unit, right? The unit here goes to n in there. But at least it's an abelian group. And what is this abelian group? It is really true that it is dual in some formal sense, and it's called Pontryagin dual. But you can also somehow
Subgroup of Q or Z.
right. So first of all, it's QP over ZP. But since we don't really know what are these guys, we can describe it in more conventional terms. So it is embedded into Q modulo Z, absolutely. And who are? What is the image? Right. Mm-hmm. Yes. Mm-hmm. The denominator is a power of P. Okay. Fine. And now you somehow make this diagram two-dimensional. I don't know, maybe let me write it right here. So you embed this into Z modulo M squared Z, but well, this projects still to Z modulo MZ. You embed this into Z modulo M cube Z. Embed this to Z modulo M 4Z. Okay, and you continue with these embeddings like this embeds into Z modulo. Only I don't want my N anymore, I want P. P. So it'll be P squared Z, and it projects onto Z modulo PZ, and this embeds into Z modulo P cube Z, and it projects here, and so on, and so forth. So QP will be the co-limit of those limits okay, if you wish a formal definition.
What does it mean?
Yes. Well, but you told me that you know what is a limit and co-limit. Of such a diagram, and then you take the same diagram but just shift it once to the right, and you have an embedding like this, and then again you shift it once to the right, you have an embedding like that, and so on. Yeah, so you first consider the limit in the rows and then co-limit in the columns. Well, I don't know, co-limit of limits of the rows. Okay. In fact, you can switch those limits too, but then if you first perform the co-limit, you will lose your ring structure. So, I mean, at the level of groups, you can switch the limits, but at the level of rings, you rather do it like this.
Why would you get ring come from this situation?
Because it's the localization. It's just if you well. If you think of what is adjoining 1 over p, it's just that. I mean, dividing by p just shifts your sequence to the right, like that. I mean, if you take some sequence, whatever, a0, a1, a2, and so on, point, and then divide it by p, then you get a0, a1, a2, and so on. You just shift your point to the left.
Okay,
Just as with usual, with our base 10 system, we do the same thing. When we divide by 10, we just shift the pointer to the left. The same here.
А будут ли эти вложения, которые после
Yes.
первого предела вложения колец?
No, you see, when you consider this stage, you do not add polynomials in 1 over p. You just add 1 over p once. So only consider, when you do this first stage, you only consider the numbers which have only one digit, possibly one digit after the pointer. And suddenly they do not form a ring. For example, if you consider 1 over p and want to multiply with 1 over p, this will be 1 over p squared. But it does not lie in denominator exactly p. Okay, so at any level, you do not get the ring. Only after the co-limit you get the ring. Okay. Now, how can you think about it? So in the very beginning, I proposed that p-adic numbers form a completion of usual numbers, rationals, or integers with respect to some norm or distance. And what is this distance? So the distance or metric on, say, z p, and then we will extend it to qp. Maybe let us somehow depict this inverse system, maybe for p equals 2, otherwise I'll have to draw too much. So I have 2 points in the last step in here, z mod 2z, but then over each of them, well, maybe they all project to 0, but each of them can be obtained from 2 points in here, right? And in turn, each of those 2 can be obtained from 2 points at the third stage, and so on. So the whole thing looks like a graph which extends infinitely far to the left. Okay, and so on. Well, this is one way to to view the two-adic integers. And now, I mean, what is a particular two-adic integer? It's a path in this graph, right? p-adic integer is a path in such a graph, infinite path. So you start necessarily from here and go to the left, but well, as I said, if you by any mishap did not start at the very rightmost point, you can always continue to the zero. But so you might start say in any infinite path or infinite path from this particular rightmost point to infinity. Okay, so now I want to introduce a metric on such paths. And certainly you do know what I mean, but just please tell me explicitly what is this metric.
Maybe the distance between two paths.
Yes.
Is the length of their intersection.
Right. So the distance, well, it's p-adic distance between two paths. Well, how do I say it's a0, a1, a2, and so on. Oh, there is a point in the end, and here b2, b1, b0, and there is a point in the end. Well, it is some function of the position where our two paths start to diverge. Okay, so they necessarily start from this point, and then, well, one can go up, another can go down. Then they will diverge at the very zeroth, so to say, point. So, well, let's call it, I don't know, x, or maybe k. So, k is the number of position such that a0 equals b0, a1 equals b1, and so on, ak equals bk, but then they start to diverge. Ak plus 1. You want here k minus 1. Okay. Okay. But fine. So they start to diverge from the point k. No, right. But you want to do something with this k. So what do you want to do with this k?
I know this answer.
You do know.
I know the answer.
So please tell me. Right. So is it right?
Yes.
I mean, for example, if k is what? It's at least k is at least what? Can it be 0? It can. Yes. So this is minus 1, so to say. They can diverge already at this point. So k can be 0. It's p to the negative k. Absolutely. But this p is somewhat dubious. You can write any number. For example, the usual base of logarithms, something like this. Any number will fit, but it's customary to put really p for some global reasons. When you want to compare all the possible p-adic metrics and also Archimedean metric, then it's convenient to have exactly p in here. But for the purposes of this particular one ring or field QP, it's immaterial. You can put any base here at all, as long as it's bigger than 1. This thing should be bigger than 1 and nothing else. We will see this in the Ostrovsky theorem. No, unfortunately. Oh, sorry. Sorry. We will not see anything at all today. Sorry. Okay. So there is this metric, and then certainly you have the projection from Z into ZP, right? Because given any integer at all, you can project them to all those quotients, and so it defines a projective system. Okay, and then I wonder what is this induced metric on Z? What is it? Just I take any element, whatever, x, and I take x modulo p, x modulo p squared, and so on. Okay.
Возможно, если у нас есть целое число, мы его записываем, а там просто схему нули вписываем.
No. No. Yeah, so the distance, p-adic distance from one x to another x certainly will be the p-adic distance from 0 to x minus y. So I mean it's invariant with respect to translations. So and this will be the so-called distance, well, the norm of x minus 1, the p-adic norm of x minus y. Well, let's denote x minus y by z. So what is the p-adic norm of an integer? Well, you write down this integer as the product of p to some power k times some other integer, whatever, t, and t is not divisible by p. And then the p-adic norm of z is p to the negative order of z, and this is k. Okay, if you just rewrite this in terms of those projections of z, you will get that. And then it extends to q, namely, now you write z equals p to the k t, and now k can be negative as well, but t is a fraction whose numerator and denominator are both prime to p. Okay, and then the formula will be the same. The p-adic norm of z will be p to the negative k. But now it can be big, right? If z has p in the denominator, the norm grows bigger and bigger. So it's somewhat opposite to the usual Archimedean intuition. having big power of p in the numerator makes your number p-adically close to 0, and in the denominator makes it p-adically far from 0. Okay. And now, due to this property, we have the non-Archimedean well, triangle inequality that the norm of x plus y certainly it's less than the norm of x plus the norm of y. In fact, if you just multiply them, then clearly by the very definition, it will be the product of their norms. That's clear from the definition immediately. And this is the usual triangle inequality. But this is somewhat, in the p-adic case, it's stronger. And what does it say in the p-adic case? Yes. So if norm of x is bigger than the norm of y, then the norm of x plus y will be equal to the norm of x. It's not just smaller than the maximum, but it's equal to the norm of maximum if they are different. But if they are the same, it may be, it's just what you said. So if the norm of x is equal to the norm of y, then the norm of sum can become only smaller. The norm of x plus y is at most the norm of x. So in other words, all the triangles in the p-adic world, plane, whatever, line, are isosceles. So the two of the side lengths are equal, at least. Maybe all the three are equal. At least two are equal. Okay. And now I just want to formulate something so that you, at least formally, will be able to understand the home assignment problem. So QP is a so-called totally discontinuous with this metric. Means it has no continuous, totally disconnected. Totally disconnected. Okay, so it contains no connected subsets at all. And just let us classify classify the balls in ZP. So a ball B, say it's an open ball, so with a radius strictly less than r, and with the center in A. If this A is a sum like this, A0 plus A1P plus A2P squared plus so on, plus AN P to the N plus so on. And here AI is some representative modulo P, like this. Okay, let us also rewrite it as this interval, let's call it partial sum Sn plus something else. Okay. I mean, it will depend only on this part, and that's the consequence of this totally disconnected property. So I assume that R is between P to the negative N and P to the negative N minus 1. Maybe like this. And then I claim that this ball only depends on this part. If I shift the center, so to say, by some small, comparatively small p-adic number, then the ball will stay the same. So B less than R of A will be equal to the B less than R of Sn. And this is the consequence of this non-Archimedean triangle inequality. Okay, because I don't know. I shift the center in some negligible way, and the ball stays the same. It's A and this is S. But the balls are the same. Okay. So it implies that if you fix your radius, there are only finitely many balls. For example, if the radius is 1, there is only just one ball, the whole ZP. There is just one ball of radius say less than p. Well, how should I say this? Of radius maybe r, where 1 less than r like this. Okay, and this ball is just the whole of ZP. And there are p balls of radius 1 over p. Okay, or maybe I should say of radius r that is bigger than 1 over p, but smaller than 1. Okay, and so on. Then p-squared balls of smaller and smaller radius. This way, the whole set of p-adic balls is a free monoid MP in the alphabet 0, 1, and so on, p minus 1, or digits. So the length of your word is the radius of your ball, maybe exponentially. So the unique ball of radius 1 corresponds to the unique word of length 0. Okay, then there are p balls of length, p words of length 1. There are just letters in your alphabet, and they correspond to the balls of this radius, essentially 1 over p, and so on. Okay, and I hope with this you will be able to understand the problems in the home assignment, and I will send it out tonight, and we'll continue in a week. Pardon me? Yeah, just yeah, right. Приписывание слов. Yeah, concatenation, right? No, it makes no sense. It's just the classification of balls. Not that the operation of concatenation of words makes no sense on balls. It's just classification of all the balls. Okay. So in fact, the home problems, they well, somehow they're about topology of p-adic numbers, and we'll talk more about it next time. But formally, you can solve your home assignment without anything else. Maybe still let me give you out some pictures that will be really. Maybe I'll give you out next time. Okay. It's about the fractal nature of p-adic numbers and the corresponding Cantor sets. So it looks pretty appealing. Let me give some explanation